All right, good morning, everybody. So I'm just going to finish off the previous lecture. There's just a few lecture slides left. So we were talking about bounded wildcard types in a generic type. We saw an upper bounded wildcard in the previous lecture. We just started talking about lower bounded wildcards. And so if you have a lower bounded wildcard, what that lets you do is it lets you restrict your type to be a supertype of the lower bound. And so lower bounded wildcards are useful when a variable in one of your methods is a destination for data. And so we had this method push all that used to look like this. So this is for a stack, but for a queue, it's the same thing, right? You'd have in queue all. You have a source collection, you have a destination stack. You would like to add the elements from the source to the destination, right? And so in our previous version of the method, our types matched exactly. Right? Now the problem with this, so the method is correct as it stands. It's less useful than it could be. If you have elements of some type T, right, you should be able to store them in a stack whose element type is either T or it's a supertype of T. Right? So for example, if you have a stack of object and a collection of string, you ought to be able to put the strings onto that stack, right? Because strings are substitutable for object. With this particular method, it doesn't work. Right? So the caller can't use this method to solve that problem. Right? They have a collection of string and a stack of object. This method won't let you. This method won't work. If you pass in a collection, so let's say a list of string, right? Then the T here has to match the T there. So string and string, and that's not the case, right? So while the method is correct, it's less restrictive than it needs to be. Right? And so the solution here is to use a lower bounded type in your destination. Right? So the destination is what we call a sink of data. Right? And so if you have a sink of data, it's often useful to make the type be a lower bounded type. Right? And so question mark super T simply says, look, your stack can have any element type as long as it's a supertype of T. Right? So if T is string, right, then your stack can be a stack of anything as long as the anything is a supertype of T. So if you have a stack of object, now this works. Right? And that makes it a little bit more useful for users of the method. And so the lower bounded wildcard type, that's the thing that shows up quite a lot, actually. If you look in the collections class, or in this case, is this collections? Yes, this is the collections class. So there's a binary search method in the collections class that lets you search a sorted list, right, for some element type T. Right? Now, if they had written this as binary search list T extends comparable T, then what that would say is that you could binary search a list of elements as long as the elements implement comparable for their type. Right. So if you had a list of, excuse me, if you have a list of object and you wanted to search it for a string, right, that won't work. Right. So if this had been T, and so if there's been no question mark here, and this had been T extends comparable T, right, you're in the same situation that you were in before, right? That's a string. That's a list of object. I ought to be able to search the list for a string because the string might be in that list, right? But that wouldn't work. And so that's why the lower bounded wildcard is used here. Right? You might wonder why it shows up in the comparable part, right? And that's because you have the same issue with comparable. So imagine that you had a list of, if you had a list of some kind of counter. So say you had a list of stopping counters and you wanted to search that list for a particular counter, right? Oh, sorry. Sorry, you wanted to binary search that list, right? If you didn't have this lower bounded wildcard here, you would be stuck, right? Again, for the same reason, right? Because of inheritance, this lower bounded wildcard becomes useful to have. Right, and that's it for the, I guess, for the strictly generics lectures. And so there's the last set of slides. that I have prepared for the course. Okay, and so this is a topic that probably should be taught more often in undergrad, but isn't, at least not here, not anywhere else I've been. So there's this, there are these things called design, oops, sorry. There are these things called design patterns, right? So a pattern is just something that frequently occurs, right? Occurs over and over and over again. So in software, there are design patterns, right? There are problems that occur over and over and over again that have a known solution. And so starting, I guess, in the 90s, people started to catalog these things. So there's a very famous book called Design Patterns that was written in the 90s that started all of this. And now there's thousands of these things. If you talk to employers who employ students who end up being essentially developers, one of their big complaints is that the students come in, they don't know any design patterns. All right, so this is from last year. So this slide looks a little bit funny. So last year, for one of the labs, this was one of their inheritance labs, inheritance/interface labs. They had these two classes, bisection and Newton. So let's just jump into Eclipse and take a look at these. Okay, so last year they were asked to implement a couple of classes that can find the root of a function, right? A one-dimensional function, right? So f of x. So there was this interface called root finder, right? And the root finder has a method called root, right? Root searches a function, right? So this f is some f of x, right? For a root of the function, right? So when f of x equals 0, and it searches a range between a and b, right? So in other words, you can search, say, for the root of some function f of x between 0 and 15, or minus 10 and 20, or something like that. Right? And it returns a root object. The root object contains the root, contains the value of the root. I forget what else it contains. It contains something else. Let's take a look. Oh, it contains the value of the root, and it contains a field called hasRoot. That's true if there is a root between a and b, or if the value actually represents a root of the function. It's false otherwise. Okay, so I asked them to implement a couple of classes that can find a root. So this is Newton's method. Now, root finder is an interface, right? So in order to actually make a root finder object, you need to create a class that implements the interface. So here Newton implements the root finder interface. And if you look, there's no fields, right? There's a constant, which is fine, right? And then all there is a method. If you know what Newton's method is, this is just Newton's method. If you don't know what it is, it doesn't matter, right? It's just a method, right? And that searches for a root. Right? There are some other things in this lab that were nice. So Newton's method requires that the function be differentiable. And so that's what that's checking for there. The bisection method is another method for finding roots of a function. And again, no fields. Right? All there is just a method. And so it looks a bit funny when you use this thing. Right? So to find the root of a function, you have to make a bisection object. But the bisection object has no data. Right? So it doesn't really make sense that you have to make an object, right? Objects have their own data. They have their own behavior. Different bisection objects should have different data. And yet, no bisection object has any data. So this is a bit strange. Right? So if you want to find a root, you need to make one of these objects. These objects have no state, right? There's no fields. Right? And so if something has no fields, that kind of looks like a utility class, right? And remember, in a utility class, everything's static. So can you make that method static in the interface? So that's the question. So you go back to the interface, and we can try to make it static and see what happens. All right. And so we haven't seen this yet in the course, right? So far, all of our methods in an interface have been non-static, right? So I made it static. Notice that Eclipse complains, right? And it complains. It says the method requires a body instead of a semicolon. So you can put a static method in an interface, right? But if you do, it needs an implementation. That's going to be a bit awkward, right? So how do I implement this thing? if I don't know what kind of root finder I want? The answer is it's awkward or impossible, right? So that doesn't really solve our problem, right? So that didn't really work. You can make a static interface method, right? Doesn't actually solve the problem in this case, right? It turns out that static methods behave funny under inheritance, right? And so they don't behave the way normal methods do. So in other words, they're never dynamically dispatched. Right? So remember, the way you call a static method in Java is you use the name of the class to call the method, right? And so the correct way to call this method for the Newton class, I would have to say Newton root, right? And for the bisection class, I'd have to say bisection root, right? If I try to say the interface name, right? So if I try to say root finder one dot root, right? That doesn't actually call a particular, that doesn't call a Newton a root finder method, and it doesn't call a bisection root finder method, right? It's going to call the static version belonging to root finder. So that doesn't really help us. You also can't override a static method. This is something else I didn't tell you, right? Not even when you use inheritance, right? If you try to override a static method, so first of all, Eclipse will complain if you put the @override tag in. But second, all that ends up happening is that you don't actually make an overridden method. What ends up happening is you make a new static method that belongs to the subclass. And so the static methods don't behave the way you want them to in inheritance. All right. So making the method static didn't seem to really solve our problem, right? So is there a way to solve our problem without making the method static and without having to make an object, right? Again, this is the problem that we're trying to deal with, right? I don't want to have to make a bisection or a Newton object because it doesn't make sense, right? So is there a way to solve this problem? Let's go back here. So let's take out our, let's change our method back to being non-static in the interface. Right, and go to, we pick one of the classes. Let's go to Newton. Right, so there's our overridden method. And so what if we put in a static field here? So public static. Okay, so I want to avoid making objects because, or I want to avoid making multiple objects, right? I don't need 10 Newton objects. Any Newton object will do, right? Because all it has is just a method. Right there. It's complaining. It's complaining because of my error up here. Right. So instead of making multiple objects, right? Why don't I make one object? So why don't I make one Newton object? That. Right. Public static Newton. I'm going to call it instance. That. I might as well make it final while I'm here. Right, because the state of this thing never changes anyway, right? And I don't want to reassign a new object to instance, right? Okay, so does that work? Right, so what does that do for us, first of all? Right, so first of all, it makes one object, right? This is static, so there's exactly one copy of this field in the entire program, right? That means if I just use instance every time, there's only ever one Newton object. So there's no longer multiple objects. Right. So now what does this look like when you try to use the code? Right. So here, instead of making a Newton object here, right, I can just write dot instance, and away you go. Right. So Newton instance is the one Newton object. Right. It has a root method which I can call. Furthermore, root is our root method is also non-static, which means it's going to behave polymorphically, right? So in other words, I can write a method that takes in any root finder object, that takes in any one of these, and I can just pass it the instance from Newton, and that will work just fine. It'll end up calling the Newton's roots method. And so it looks like this might be, oops, sorry. Come on. It looks like this might have solved our problem. So static instances, it turns out, are common in the standard library classes. Common. Are they common? They're not uncommon. I guess that's the best way to put it. So if you look in a class like color or Boolean, so in Boolean, you're in the same situation with Boolean, right? Boolean is the wrapper class for little b Boolean. There's only two Boolean values, true and false, right? So it doesn't make sense to make a bunch of Boolean objects. You only need two. So if you look at the Boolean class, there's a static field called true and there's a static field called false, all uppercase, that represents true and false, right? So those are the two Boolean objects corresponding to true and false. Right. The color class has a bunch of static objects in it as well, right? So it has a class, it has an object called black, it has an object called white, it's got one called red. So for, I don't know how many common colors there are. For some relatively small number of common colors, there are just a bunch of static constants that represent those colors. And they show up in string and collection as well. Again, so why are they used? So it's to restrict the number of objects that are being created. Right? If you don't need multiple objects, there's no point in spending the memory to create and store those objects. Okay, so this is for bisection, but the same is true for Newton, right? So here I've got my static instance, right? If I'm careful when I'm writing my code, or if the users are careful when they're writing their code and they always use instance, everything's fine, right? However, right, so in other words, if you always write this, instead of making a new object, everything's fine. However, there's at this point, right, there's nothing stopping anybody from actually making a new Newton object right there, right? And then calling root using their new object, right? Why is there nothing stopping them, right? So if you look in the class, there's no fields and there's no constructor, right? And so remember what happens if there's no constructor, right? If there's no constructor, then the compiler sneaks one in for you, right? So in other words, the compiler sticks that in for you, right? Which we don't want, right? We don't want people to make any objects of this type. So what's the solution? Make it private, right? And now, well, inside the class, I can still make a Newton object. So this still works in here, right? But outside the class, no one else will be able to actually make a Newton object. And so what have we done now? We've created a class, right, that behaves polymorphically, right? It has non-static methods, but there's only ever one instance of the object. That's kind of cool, right? So we now have a static instance and a private constructor, right? What have we done? We just quote unquote discovered a software pattern, right? So this is called the singleton design pattern. Once again, a software pattern is a general reusable solution to a commonly occurring problem within a given context in software design. The singleton pattern restricts the instantiation of a class to a singular instance. In other words, it lets you make a class where there is an object, but there's only ever one of them. And so it turns out that there are many instances in a software, in a piece of software where you might want to have only one particular object of a certain type. Right. So for example, you might only want one way to access a central database, right, or something like that. There's some centralized resource that you want to control access to, right? And so you only want one object accessing that instance, accessing that resource, sorry. Right. The pattern gives you easy access to the object, right? So to get access to our Newton object, it's just Newton.instance, right? Everybody can access it because it's public, right? And it controls how that object is created, right? So in our Newton class, right, our Newton class creates the object when it gets loaded into memory. That's how it works. So that's how static fields work in Java. So when you load the class, that thing gets initialized, right? But it's possible, remember, you have constructors. So it's possible to control when this thing gets when this thing actually gets created if you need to do so. Okay, so there are variations on the way this thing works, right? This is just one particular way to implement a singleton in Java. So we have let's look at our method here. We've got a public field, right? Public static final field that represents the instance, right? You don't have to do it this way. There is another way to do this. So the other way to do this is to create a public method that returns the instance. Come on. That, right? You now make this private. Right, so hide the instance from everybody so they don't access it directly, and instead they access it through a public method. So yeah, instead they access it through a public method. You might want to do it this way if you need to control when the instance gets created, right? So if, for example, it's very expensive to make this object, right? Then you delay making the object until somebody actually asks. Right? So that would be an example of when you might want to use this version instead. Finally, the preferred way to do this in Java is to use an enumeration. Right? So remember how enumerations work in Java? So an enumeration in Java is just a class that has one or more constants in it. Right? The language guarantees there's exactly one of each of those constants. That's exactly what we want in this case. Right? We want exactly one Newton object. So you can just make an enumeration. Right? One of your constants will be the root finder object. So you give it whatever name you want. Right? And again, an enumeration is just a class. So you're allowed to add methods to the class as well. So you can just turn this class, the Newton class, right, into an enumeration instead. Right? Now you can get rid of all of this stuff here. Right? You just put in your constant and away you go. Right? You put in your constant, you put in your method, and you're good to go. And so the enumeration method does have some obscure advantages in Java. They're not the advantages are not relevant to us. It is the preferred way to do this, though, if you ever find yourself in the situation where you need to make sure there's exactly one object of some type. So that was kind of neat, right? So that's a simple little design pattern that's understandable to people who have taken their first Java course. Okay, so you can riff on this particular design pattern. So the singleton says there's exactly one instance of a class, right? Now suppose that's not exactly what you want, right? So you want something that looks like a regular class. Right? So in other words, you can make objects. But whenever you make an object, you would like there to be exactly one of those objects, right? So each object has its own state, right? And you want every object, and each unique state has exactly one corresponding object. You might think, well, this is a bit funny. Why would you ever want to do this, right? And so remember, there are these wrapper classes in Java, right? So integer is the wrapper class for int, right? It doesn't make sense to make a new integer object every time you make an int, right? So for example, you make a list of integer, right? You put a bunch of ones in the list. Right? It doesn't make sense to make a new integer object every time for every value equal to 1. Right? Value 1 is 1, it never changes. So it'd be nice if you could make sure there was exactly one integer object whose value is 1. Right? And similarly for 2 and 3 and 4, right? You don't want to make all of them. You don't want to make all 2 to the 32 integer objects, right? But you might want to make a small number of them. And that's exactly how the integer class works in Java. It defines, I forget what the number is. I think it's 128 or something like that. So if the value of the integer is small, it makes one integer object and stores it somewhere. Every time you use that value, it just recycles the object. So this only works if your objects are immutable, right? If your state can change, then this is not going to work, right? So your state has to be fixed here. Okay, so how does this thing work? So I want to manage, so basically you want to make a class that manages its own instances, right? It manages its own objects. So you need some sort of data structure in which you're going to store these objects. Okay, so back here. So what are we trying to do? I want to make sure there's exactly one object per unique state, right? So that per unique state part, right, means that the state can be used as a key in a map, right? So remember how maps work, right? Maps map a key to a value, right? Where all the keys are unique, right? So if we use our state for our key, we can make a map, right? Our map is going to manage all of the individual objects. Right? So each entry in the map is the state mapped to a particular object, right? That represents that state. Now, you only want one of these maps, right? You don't want multiple maps that have that contain multiple mappings from state to object, right? You want exactly one of these, right? And we know how to do that, right? We can just make a static field. Okay, so I forget what the example is here. So let's cook up some class and try this out. Go away. All right, there you go. I need to make a little project somewhere. I'm just going to reuse this project here. Okay, so we're going to make a class. Okay, so let's make a class called myInteger. All right, so this thing is going to be, so this would be a, this is going to be a very quick implementation of Java's integer class. Okay. So we want to, so the idea here is that we want to make sure there's exactly one myInteger object for each int value. Okay. So public, so I need a, so every object is going to have its own value. The value. Right. Inside of our class, we want our class to maintain a mapping from each integer value to an object that represents that value. So I want a map of some kind, right, that maps an integer to a myInteger object. I want to make it static because I want there to be exactly one map. Okay, so by making a static map, I have to initialize it somewhere, right? I guess I might as well do this the correct way. So let me make it final as well. Private static final, so that I don't replace the map accidentally. Final map equals. So I'm going to use a hash map for this, but you can use whatever map you want. Sorry, hash map. Like that. All right, so there's our map. Okay, so now we need a way to access the values, right? And so in the Java integer class, there's a method called value of. Let's do that. So public static value of int. Right. So this method here, oh sorry, is going to return the myInteger object whose value is equal to that. Right. So it's going to return the myInteger object that represents the int value. Right. So where are these things being kept? Well, they're being kept in the map. Right. How many of these things am I going to make? So it turns out that we're going to do this is we're going to make a myInteger object only when we have to. Right. So what we're going to do is we're going to look in the map for this value. Right. So get value like that. Right. So I'm going to look in the map for this value. Right. Does that object exist? Let's do if obj is not null. Okay, so if it's in the map, I can just return the object. Like that. Right? If it's not in the map, now I have to make a new myInteger object whose value is equal to value. Right? And so now I'm going to do myInteger. Oh, now I can do obj equals new my like that. Right? So I need to make a new object, so I need a constructor of some kind. I don't have one yet, but that's what I want to write. So we'll put that in next. Right? So I make the object, I stick it in the map so that I can remember it for the next time someone wants that object. Right? So map.put value obj. That, and then return obj. But, right? And now I need a constructor. Right? Now, remember the point of this class, right? This class is controlling access to its instances. Right? If someone wants the myInteger object equal whose value is 2, right? They have to go through the value of method, right? In other words, they shouldn't be able to make their own myInteger object, right? If they are, there's no way for me to know it. There's no, so yeah, I don't want multiple objects equal to 2, right? So that's what we're trying to do here. So I need to control the construction of objects, which means make the constructor private. That, right? And away you go. Right? And so that class there guarantees there's exactly one myInteger object corresponding to every unique int value. Right? And this is, and it's not exactly the way that Java implements the integer class, but it's pretty close. Java uses an array to hold the objects, and it only keeps the first, I forget how many, it only keeps the first 128 or something like that integers in memory. Right? If you need one that's outside that range, it just goes ahead and makes a new object every time. Okay, so that was kind of neat. So what did we just do? Right? We've just created a class that guarantees there's only ever one object for every unique state for that type of object. So that's the multi-tin pattern. Right? So a multi-tin allows for the controlled creation of multiple instances, right? But there's only ever one of each one of those objects, right? Each object corresponds to a unique state, right? And there's only one object for each one of those states. And so this is what you would use if you needed something that looks like an enumeration, but you don't know what the constants are for the enumeration ahead of time. Right, so remember, enumerations are what you use when you have a fixed and finite number of instances that you know ahead of time. Right, if you don't know what the objects that you want are going to be ahead of time, you can use the multi-tin pattern to do that. Yes.
So with the extent that
Yeah. Yeah. So I haven't looked to see how they actually implemented it. It's not a singleton because there's two unique states. So it could be a multi-tin with a number of unique states. It's 2, but I'm not exactly sure how they implement that class. Okay, so the multi-tin, that idea of making a map or some other collection and storing objects in it, right? And then retrieving them when you need them, because that's basically what we did, right? That's all we really did. I've got a map, right? Every once in a while, I make a new object, stick it in the map, right? When someone needs an object that corresponds to one of the objects in the map, we just return that object. Right? So the idea of storing objects and retrieving them when you need them, instead of making new objects all the time, is called caching. Right? So a cache can be hardware or software, right? You have your CPU has many caches in it. Right. So it's a component that stores data so that future requests for the data can be served faster. Right. So your CPU, a modern CPU probably has 3 or 4 different memory caches. Right. Each one is each one is slower as you go up the higher. It's faster as you slower. You have a small cache that's very fast, so it's close to the registers in your CPU. You have another cache that's slightly farther away, it's slightly slower. You have another cache that's farther away, again, it's slightly slower, but it has more memory, right? And then finally, you have main memory, right? Your memory sticks in your computer, which are very far away from your CPU. And it takes a long time to retrieve data from one of your memory sticks, right? Long for the CPU. Okay. So all of the Java's integer wrapper classes, right? So the integer short, I don't know if car does it or not, or character, but all the integer wrapper classes and the string class, they all cache instances of their objects. So string is funny in Java, right? So in your program, if you write a string literal, so anything inside double quotes, the string cache remembers what it is, right? So it caches that somewhere. It's got some data structure that remembers what are all the literals that have been used in the program. If you reuse the literal again somewhere in the program, it just looks up the literal in the cache. And so that's why when you use equals equals in a Java program to compare strings, right? And your program is just a little simple program that you haven't really is the typical simple test program that you might write in a first year Java course. It seems to work, right? It's because remember what equals equals does, it checks whether two objects have the same memory address, right? And that seems to work because the string class is caching all of your literals, right? So if you write string h equals high, and then somewhere else string j equals high, it turns out they're both the string. They both refer to the same string object because the string class is playing this trick of caching all the literals. Yeah.
It's caching stored between instances of running the program, or is it just like?
No, it's not. Yeah, it's not persistent. You can have a persistent cache, right? So you'd have a database of some kind. Right.
That requiring.
That requires some other external, mechanism. That's right. But it's absolute. You can absolutely have an external cache. All right. Turns out there's literally thousands now of documented design patterns. I've only shown you 3. So you can go on and on and on and on. I don't know if there's anywhere in your undergraduate curriculum where you will learn about these things. I know for a fact computing science students do not learn about them. It's kind of bad. But if you're interested in software development, at some point you're going to want to start looking around and Googling design patterns and see what comes up. Turns out they are quite important. The problem with them is that they're domain specific. So if you go out and do some web programming, there's a bunch of web programming design patterns, right? If you go out and do game development, there's a whole bunch of game development design patterns, and so on and so on and so on, right? So that's just a little taste of what's out there outside of academia. All right, so I guess that's going to be it for today. Next week, I guess the plan is going to be, I guess I'll take up one of the old exams on Tuesday. And then I'm not sure if there'll be a Thursday class or not. But we've covered quite a lot of ground in this course. So I'm not upset that we're done ahead of time.